We've talked about slope, we've talked about linear equations or linear functions. And now we're going to talk about the slope-intercept form of linear functions. So there's more than one form. We've already gone over the standard form before. Ax plus by equals c. Just as a reminder, x and y are the variables. A, b, and c are numbers that just change based on which equation we're looking at. Now the point-slope form is one we haven't done yet, but we will later. So since I was just listing forms, I put it here. So you don't have to understand it or use it yet, but I'm going to go ahead and tell it to you. It's y minus y1. That y1 is just the same kind of y1 as we used in the slope formula. So it's a subscript, not an exponent, equals m times x minus x1. So we'll explain that later when it comes up. But for now, just wanted you to write it. But this one, the slope-intercept form, that is our focus today. And its form is y equals mx plus b. So the huge benefit of the slope-intercept form is just by looking at the equation, you can quickly identify the slope, because that will be the m, because it's the coefficient. It's the number in front of the x. So just by looking at the equation, you'll know right away, oh, the slope is that, because it's the number staring at you that's right in front of x. It also tells you the y-intercept. That's the b, so that's the constant, the number by itself. So just to let you see an example, we're not going to work this problem at the moment, just wanted you to see this is an equation in slope-intercept form. So just by looking at this, I know right away the slope is 3. And the y-intercept is -2. So if there's a minus sign, you treat that as a negative. So the slope is 3, and the y-intercept is -2. So here's cool part number 1. If they tell you the slope and the y-intercept, you can very quickly write the full equation of the line. See if I can get this a little clearer. I think it's a little better. So you remember, y equals mx plus b, is our general form for the slope-intercept form. So all you have to do is take the slope, plug it in for the m, take the y-intercept, and plug it in for b. And just like that, you have your equation. So we'll do the same thing on number 2. We have our slope, y equals 4x, because the slope goes in front of the x, and our y-intercept is 1. So you can write plus -1, but it's more efficient to just write -1. It's not wrong if you write plus -1, but I'll always just change it to a minus, because they'll do the same thing in the book and all that. So the slope on this one is 3/5, so we write y equals 3/5 x. And the y-intercept is -2, so we write -2. For number 4, the slope is -3, so we write -3x. And the y-intercept is 2, so we write +2. So when the y-intercepts are positive, you write plus that number. When the y-intercepts are negative, you write minus to represent that negative. So that's the first cool thing, how quickly, with those two pieces of information, we can write an equation. Cool part number 2. I know we learned how to graph an equation in this chapter by using the x and the y-intercepts, and from what I could tell, you guys thought that was pretty straightforward. Then we could also do it by making a table, which in general people like that less. But here I want to show you how you can actually do it pretty quickly when you have the slope-intercept form. So always, always, always begin with the y-intercept. So you look at this first one. We looked at this one earlier. Our slope is 3, but I'm not going to start with that. I'm going to start with the fact my y-intercept is -2. So I right away know one point the line passes through. It's -2 on the y-axis, because the y-intercept is the place where the line crosses the y-axis. So first thing you do on all of these, plot the y-intercept. Next, we'll use the slope And you've got to remember, slope, I've got it written here, but I kind of covered it. Slope is often described as the rise over the run, because the y values are on the top of the fraction. They tell you how far up or down you go. Sorry about that. The x values on the bottom tell you how far left or right to go. So as you look, we think of it as a fraction, and on this we might be like, well, wait a minute, 3 is not a fraction. True, but thankfully any whole number can be made a fraction just by putting it over 1. So we just change it from 3 to 3 over 1. So that slope means that to get the next point on the graph, we need to go up 3, that's our rise, then to the right, 1. So up 3 over 1. So you start at the y-intercept, don't start at the origin, start at the y-intercept, and you go up 1, 2, 3, and then over 1. Then just connect the lines. Now, just for practice, I'm going to keep going and show you how if you continue that pattern, you just get more of the line. So if I go up 3 over 1, up 3, 1, 2, 3, over 1. One benefit, you're only required to draw 2 points, but one benefit is it can help you keep your line a little bit straighter if you do more than 2, but that's up to you. I mainly want you to understand that the cool part is because the slope is constant, you can get points over and over and over just by continuing that same up 3 over 1. Now, people who write math textbooks are cruel and mean, so they'll tell you to graph it, but then they don't always put it in slope-intercept form. So this one, our first thing is actually to rewrite this equation in slope-intercept form, which really just means get y by itself, like it is over here. So to get the y by itself, I'll start by subtracting 3x from both sides. So that leaves just 2y on this side. And I'm going to put this minus 3x up front because that's the form we'll want for the slope-intercept. We want the x term first, the constant second. Now, as far as math is concerned, this is the same thing as 8 minus 3x, but that's not in the order or the form of the slope-intercept. So that's why I put the negative 3x up front. Next, we need to divide every term by 2 so that the y is fully by itself. So we get y, and then this doesn't reduce, so just leave it as it is. 8 over 2 is 4. So now we have it in slope-intercept form. So we always start with the y-intercept. It's positive 4, so I put a point up here at positive 4. Now the slope is explained right here. For the slope we go down 3, negative 3 means go down 3, 1, 2, 3, and then over 2. So I go over 1, 2. If I want to keep going, I could down 3, 1, 2, 3, over 2. You can see how that makes a nice straight line. Okay, on C, they were kind to us, and they did put it in slope-intercept form. So we start always with the y-intercept, which is 4. Then we use the slope to help us find our next point. So this time the slope is negative 1 over 2, negative 1/2. That means we should go down 1 and then to the right or over 2. So down 1 over 2. Down 1 over 2. And then the meanies do it again. We've got to rewrite this one in slope-intercept form. But the pattern is really similar if they put it in standard form to get it that way. You just move the x term over. Make sure you put it first. And then divide everything by the coefficient in front of the y. So we get y equals, and this doesn't reduce as far as the fraction is concerned, but 2 negatives do cancel each other out. So I'll say positive 3 over positive 4x. Then 12 divided by negative 4 is negative 3. So on this one, the y-intercept is negative 3. So I come down to negative 3 on the y-axis and mark that. Then the slope tells me where to go next. I go up 3 and over 4. So starting at negative 3, I go up 1, 2, 3. Go over 4, 1, 2, 3, 4. And I have my line. So that's the second cool part of the slope-intercept form. And when you're in that form, it's pretty quick and easy to graph the equation. Cool part number 3. If the graph shows you 2 points, or they may show you more, as long as one of them is the y-intercept, then you can quickly transition from the graph to writing the equation. So just like I suggested with the graphing, starting with the y-intercept, I suggest you that too. That's not as essential here. It is essential on graphing, but so we'll identify the y-intercept. So look, here's the y-axis. This line hits the y-axis at -3. So that means I know that by the b for the equation is -3. Now we use the rise over run pattern to figure out the slope. So I suggest you always start at the point on the left. It doesn't matter if it's the y-intercept or not. Just start at the point on the left and then count how far up or down and over you need to go to get to the next point. So for this one, I have to go up 1 and then over 1, 2. So up 1 over 2. So my slope, my m, is 1/2. So once I see that, I can write my equation. Y equals 1/2 x, because the slope goes with the x, and my y-intercept is -3, so I write -3. Okay, similar one down here. They give us 2 points. One of them is in fact the y-intercept. So I can see right away my y-intercept is 4, so b is 4. And then if I start there, to get the next point I have to go down 1, 2, 3, and over 1. So my slope is -3 over 1. So my equation would be y equals -3x plus 4. So that quickly, we're able to just look at a plot or a line and write its equation. Cool part number 4. It turns out there are lots of things in the real world that can be modeled by linear functions, and we'll see lots of them in homework in everyone's beloved word problems. But interpreting what the words say into a linear equation is the big trick. They're not that hard to work with, but creating one out of a bunch of words and gobbledygook, that's what we got to figure out. So just a reminder, the slope-intercept form is y equals mx plus b. So when a real-world scenario takes this form, in general, y represents your final amount or what you're looking for. The slope is the rate at which something is changing. X is whatever is changing. And then the initial amount is our y-intercept, which, if you think about it, that usually is our initial amount, because if we plug in 0 for x, we get the y-intercept. So when I plug in 0 for x, that's at the beginning, so it's our initial amount. So I'll try to explain what I mean in this first example. So in 2002, 2.8 million girls competed, misspelling there, competed, not completed, in high school sports. So right there, they gave us a beginning, a starting point. So I know, because they're giving me a starting point, that is going to be my b. So before I read anything else, I know b is 2.8. And we'll just know everything's in terms of millions, so we'll just leave it as 2.8. Now that's a set number, it's fixed. The girls who competed in 2002 can't change. The number of girls this year could change because it's still this year, but in the past, that number can change. The number of girls competing in high school sports has increased. That's a word that means change. Increase means change in a positive direction. It increased by an average of 0.05 million per year. So that's the rate of change. An increase, or a positive, 0.05. So now we can write a linear equation because we know the rate of change is 0.05, so that's our slope. And the initial amount we started with was 2.8 million. Now, they want us to use this to estimate the number of girls competing in 2027. Now, this is also an important thing. When it comes to time, we're talking about years, days, weeks, months, whatever. In general, we're not actually going to treat the beginning as 0. In other words, I'm not thinking when I plug in 0, I'm talking about the year before Jesus was born, 0 AD, which, by the way, there is no 0 AD. It started with AD 1. But anyway, I'm just saying, it's not really fruitful for us to think about how many girls were playing high school sports 2,024 years ago. So whatever our beginning time is, as far as our data, that's what we treat as the beginning. So if 2002 is what we're treating as 0, to get how many we're playing in 2003, I'd plug in 1, because that's 1 year after 2002. If I wanted to know how many we were playing in 2004, I'd plug in 2, because that's 2 years after 2002. And that's the initial amount, and that was the amount in 2002. So to find the number of girls competing in 2027, we have to say, okay, how many years after 2002 is that? And if you can't tell just by looking, that's fine. You can just subtract this later year minus the first year. And when you do subtract those, you get 25. So we need to plug in 25 as our year. Because 25 years after 2002 is 2027. Oh, sorry. Oh, there it is. Tell you what, I think I have a better way I can show this. Just a second. Here we go. Okay, 0.05 times 25. So we get 1.25 plus 2.8. So we add 2.8 to that. Try that again. 1.25 plus 2.8. We get 4.05. So that means the number playing in 2027 will be 4.05 million girls. Okay, let's look at a similar problem down here. The ideal maximum heart rate for a 25-year-old who's exercising is 117 beats per minute. So that's our initial amount. That's not going to change. For a 25-year-old, this is the goal rate, period. So our B is 117. For every year older than 25, the ideal heart rate drops 0.6 beats per minute. Okay? So that means our slope is negative 0.6, and it's negative because it's dropping or going down that many beats. So you do have to pay attention to the words to see if it's going up, in which case the slope is positive, or going down, in which case it's negative. So I would say y equals negative 0.6x plus 117. Find the ideal maximum heart rate for a 55-year-old who is exercising. So again, I'm not going to plug in 55 because I'm treating 25 as my starting point. So this is 30 years after the 25 year. So I put 30 in. And once you plug that in, you will get negative 18 plus 117, which means their maximum heart rate when they're exercising at that age should be 99 beats per minute.